Alright. That looks normal. I don't see, like, a crackling static in the background, other than what the music is playing, which I'm winding down now. Okay, so, like all computer-related issues, turning it off and on again fixed it. However, the strange part about that is literally my Monday, like, order of operations. First thing I do, reboot the computer. So I rebooted it. So I've already done the turn it off and on step just to, like, so my Photoshop won't be garbo. But for some reason, Windows did not detect my microphone on my headset here, nor did it detect another headphone feed. So it was only detecting 1/3 of my headphones. And I have no idea why that was. So I rebooted everything. It popped back up. Everything should be working now. I'm going to chalk it up to Gremlins and or Maya. Where is Maya? Maya, where are you? I don't know. Okay, so I apologize for that. So let me go over that whole thing that I said that nobody heard earlier. Happy to meet everybody on Friday. I am just as awkward in person as I am on these streams, like even more so now. When we were in the lab on Friday, I noticed something about the standard solution that everybody was preparing. The absorbance that people got seemed to be really, really, really high. Like almost twice as high, I guess, as I was expecting it to be. So if you are doing your calculations for lab number 1 for part B, and you get a K equilibrium constant of, like, I would say 30 to 50, that's totally okay. I realize that we tell you the answer at the end. I want to say it's like 140 or 170 is, like, the literature value. It's in the post lab. I don't think people are going to get those numbers with the experiment. Don't worry about that too much. So if you get a number between 30 and 50, that is the same number that I was calculating when I was inputting everybody's solutions into my computer. So totally fine if you get that. Just cite in your sources of error, like, oh, well, if this is too big, then, and try and explain it the best that you can. Further, the numbers in the calculations that are used are very logical in the order in which they're obtained, but I do know that students tend to get lost in the calculations a little bit. And there is one situation that comes up for, I think, calculating the standard. So if you calculate the wrong standard, then you get, like, a series of increasing equilibrium constants, and you don't converge to a number. If that happens, you're making a calculation error. In any case, if you get stuck, let me know on Discord, because I can walk people through it. That is the entire point of the Discord channel, is, like, if you get stuck on a problem, homework or lab or whatever, and you need help, you can walk each other through it. The royal you, so that includes myself, so I can help you as that comes up. I'm more than happy to do that. Okay. Yeah, we're gonna have to go a little bit over today, so I apologize. The video will end a little later than we normally would because of the 15 minutes of technical issues that I wasn't even aware I had because I didn't do a mic check. Oh well, that's what you're supposed to do. All right, where we left off on Wednesday last week, we were working with this equation. So we said, okay, if delta G represents whether a reaction is spontaneous or not, then 0 being the point where we go from a negative spontaneous reaction to a positive non-spontaneous reaction, 0 must be the middle of those, i.e. equilibrium. The reaction doesn't proceed in either direction. It is already at equilibrium if delta G is 0. So we said, okay, well, if I set delta G to 0, I can then solve for T here, and I can find what temperature a reaction would be at equilibrium. And then I could figure out, is the reaction spontaneous above or below this temperature? So that's what we did last week. So what we're going to do today is we're going to play around with this a little bit more. And if this will advance, there we go. Let's look at this expression. At what temperature would delta G equal 0 for the boiling of water? And you should immediately know the answer. without doing any thermodynamics. You could just type it in the chat if you know the answer. At what temperature is the boiling of water spontaneous? You don't even need to take a chemistry class for this, right? Duh, it's 100 degrees, right? That's the temperature at which water boils. Yeah, there you go. If you heat water to 100 degrees, it will spontaneously boil. In fact, that's by definition, right? So what we're going to do is we're going to do a thermodynamics calculation and see if we get 100. Now, we're not going to get 100, and the reason for that is because these numbers that we're using are not accurate at 100 degrees Celsius. They're accurate at 25 degrees Celsius. And that's what this little circle means. So let me select this real quick. So you might remember from 162 that this little circle doodad means standard. This is a thing that I did. Hold on. Every time I tap this eraser button on my pen, which doesn't actually erase, it does that. Standard state. And so what that means is that we have established a bunch of standards that we use, and if we are at these conditions, then the number that we spit out is delta H or delta S or delta G or whatever with the little circly doodle. So for instance, the heat of formation, which is all of the energy that is either absorbed or released when I take elemental matter, so hydrogen and oxygen in this case, and allow it to combine together to create water, I would release 285.83 kilojoules per mole of water that I formed in that way, if the system was at 25 degrees Celsius when I did this. Same thing for entropy. So my entropy would be 70 joules per mole Kelvin if I was measuring entropy at 25 degrees Celsius. Now, both of these are functions of temperature. So temperature is going to affect them somewhat. At a higher temperature, I won't get necessarily these numbers. But for our purposes, it's going to be close enough. And we'll just assume that these numbers don't change appreciably over temperature. So what we're going to do is we need to figure out delta H and delta S for the reaction. Now, the reaction is actually a process. We're going to go over here. Oh, I need those numbers, though. Because we're not actually doing chemistry with this, right? We're just doing a phase change. So to figure out delta H for the reaction, and again, this is a process, that's going to be the sum of all the delta H of the products minus the sum of all the delta H of the reactants. You probably remember this from 162, right? Products minus reactants, where you had to go look up a bunch of numbers in a table in the back of the textbook. And the textbook is just this, I mean, you go to a website for our online text. And you do the same thing for delta S. I forgot that delta. There we go. And because we're using standard state conditions, I'm going to just throw in all these little circly guys. So, delta H for my reaction would be, I don't have a different color selected. Hold on, let me do that. So delta H for the reaction using standard state conditions would be, so I have my products minus my reactants. So minus 241.82 kilojoules per mole minus negative 285.83. And so these become positive. Excuse me. And what do we get for delta H here? And then plus 285.83. So 44.01. Okay, so there's delta H. And we do the same thing for delta S. And that would be 188.8. Minus 70. And that would be 118.8. All right, so there are our numbers. This is positive too. I might as well indicate that. For our expression. So now what we can do is we can say, okay, so this is true. And therefore, T must be delta H over delta S. Which would be, so for delta H, I got 44.01 kilojoules per mole, which I'm going to turn into joules per mole so that my units cancel out. So that's going to be a big place where people can get stuck, is that this and this are not the same unit. So just be careful of that. So then we got S, which is 118.8 joules per mole Kelvin. The joules per mole will cancel out. Then I have 1 over Kelvin, which will equal something in Kelvin. And so when I do this calculation, I should get 373. And you're going to notice that it comes up a little short. So I get 370.5. Which is about 97.5 degrees Celsius. Now, that's remarkably close to what we would expect it to be, right? So we know that water boils at 100 degrees. So our thermodynamics checks out. We're within 2.5 degrees of the expected temperature. And the reason that it is slightly off is, again, because these numbers, which I have to go back over here to circle, these numbers are most accurate at 25 degrees Celsius, which is, again, why the little circly doodad is there. If we had numbers for 100 degrees Celsius, then we would land exactly on 100 degrees, almost certainly. So, close enough for our purposes. So if you are given a process, any process at all, and you have enthalpy and entropy data, which you do because it's all in the back of the textbook, you can figure out the temperature at which any process becomes spontaneous. Now, where is that information? I believe in your textbook it's Appendix G. So what I'm going to do is I'm going to find that real quick, if I can find the textbook, so that I can show you what that looks like. I have to scroll all the way to the bottom here. Standard thermodynamic properties. There we go. That's what I want. All right. So I'm going to give you the link for this, just in case for some reason you want to browse along with me, I guess. I don't know. So here's delta G values. That's way too big. Hold on. We do not need the table of contents. We do want this part in case. Let me see how this is going to scroll. Yeah, that's fine. All right, so this is the document that I'm looking at. And so we have delta H, delta G information, and delta S information for all of these substances. And so you can see all of these numbers for any substance that I would refer to in this class. There are a lot of substances, right? So in any quiz where you need this thermodynamic data, I'm going to say refer to Appendix G in the OpenStax textbook, because you could just look it up for any of your quizzes, and then just cite in your quiz like, oh, I got it from Appendix G. Now, if you have an exam, obviously you don't have access to this text, so I will provide you with the numbers that are relevant, okay? But for these types of problems, you'll need these numbers, and this is where you find them. All right. All right, here you go. I want you to tell me the boiling point of carbon disulfide using this data. I have fetched this from the back of your textbook already, and I have also given you an answer on the board. So your target answer is 319. So I want you to do the same calculation we did, and tell me what you get for your results. We'll go over the answer in just a second. $313.9 sounds pretty close to me. If you get within like 5 to 10 Kelvin, I think that you have definitely done it correctly. So let's do one more minute and we'll go over the answer. Now, a nice thing about this type of problem is that it's sort of hazard proof. So, now I didn't give you the actual process here for this problem. I just said verbally, tell me what the boiling point is. And we just did an example, so it's not difficult to assume that this is what you're supposed to do. But if you flip around the numbers, and so maybe you did the reverse process where you did gas turns into liquid, and so you did the numbers backwards. If you do them both backwards, the only thing that's going to happen is that when you get to this part, you're going to get both numbers are negative, which will then cancel each other out, and you get the same answer anyway, right? Now, where that will mess you up is if you have a question that's like, is it spontaneous above or below this temperature? And if you get both the same sign, but you got the wrong signs, then you'll get that part wrong. Because you would, if they're both negative in this case, you would say, oh, well, they must be spontaneous below or something like that. Below a certain temperature. Where's my pen? There it is. Okay. So delta H for this would be, and we'll put the circles in here because we're actually using standard state data. So that would be 116.9 kilojoules per mole minus 89.70. And that would be, that's going to look like 30 something, right? Minus 89.7. 27.2. And then delta S for this would be 238 joules per mole Kelvin minus 151.34. That looks like 80 or so. Let's see here. I want to round that. That's what I want to do. All right. I just want to make sure I get the right sig figs here. So now we'll all throw these numbers into this expression, and so we get 27.2 kilojoules, so that's 27,200 joules per mole, divided by 86.7 joules per mole Kelvin. Those parts cancel out, and I will get an answer in Kelvin, which will be 86.7. 313.7, or we only get 3 sig figs, so 314. That's pretty close to the actual boiling point of 319 that I looked up when I wrote this problem. Cool. So now you can estimate boiling points using thermodynamic data, which is actually really cool. Because now you know the boiling point of anything by just looking at Appendix G. Well, anything included in Appendix G, I should say. All right, any questions, let me know in the chat. All right, we talked about how water boils at 100 degrees Celsius. Now, water at 25 degrees Celsius, which is the standard state, that's why we have this little circly guy there. Here's the delta G for water at 25 degrees Celsius for this process. Now, there is actually an issue here. And the issue is this. If you spill water on the counter, it will evaporate, right? There is not like a puddle of water on your dinner table that is there when you spilled it 4 years ago, because water just never evaporates at a certain temperature because delta G is a positive number. So there's an issue here. This says that water should not evaporate. Instead, water should condense on your table. Everything should just be water everywhere. Now, there is a circumstance where this is true. This number is not invalid. This is the correct delta G. This reaction is non-spontaneous, and water should spontaneously condense at standard states. What are the standard states? Well, any gas would be 1 atm, which would be this. Are you currently surrounded by 1 atm of water vapor? I hope not. That would mean that the only thing that you are breathing is water vapor, and you would drown. That would be terrible. No, what you are breathing right now is a mixture of mostly nitrogen, 20% oxygen, and then like 1% water vapor, CO2, argon, etc. So water vapor is actually a very small fraction of the air mixture that you are breathing right now and that is surrounding you. So water will not condense at that because it's not at 1 atm. So this number is not valid for what we're currently experiencing. So how much water is actually in the air? And can we calculate a delta G for that to see if that process would be spontaneous and where equilibrium would lie? And the answer is we can, but we're going to give you a new equation to do that, and that's this. So Q in this expression is the reaction quotient. In other words, just plug in whatever the value you would calculate for the equilibrium constant at whatever conditions we provide you. And you're going to notice that that's going to give you delta G without a circle once we do that. So we're going to use what would delta G be at a standard state, which you can calculate from the back of the text in Appendix G, times RTL and Q. This R is this one. The reason being is delta G's are in joules per mole, right? So my R needs to match that. And then the temperature would cancel out this term here, so I'd get joules per mole. So if you're ever confused, like which R do I use? Look at the units. If you don't see liters and atmospheres anywhere in your expression, don't use 0.08206. Use 8.314. You're only ever going to use the ideal gas constant for applications that have a pressure and a volume in them, or that have an energy in them, energy being joules. So if I want to figure out the delta G for any reaction that is not at 25 degrees Celsius and 1 to atm and etc., I can use this equation to do that. So let's do this problem. We'll see what we calculate here. That was just saying all of the things I said about constants. So, all right. So for this process at standard states, we should get this number. And so let's show that right now. So remember that the equilibrium expression for this would be products over reactants. Well, I only have one product. And I only have one reactant, but my reactant is a liquid, so I don't include it. So this is Q. So we're going to do this. We're going to do this calculation twice. We're going to do it at standard state, and we're going to show what happens when we do that. Then we're going to show it at a more typical condition. So delta G naught plus RT ln Q. So we already know that this number is shown right there, 8.59. Actually, you know what I want to do? I want to write it like this. I always just write everything in joules per mole. All right. So let's look at this term right here. So here's R. Here's T. If we're doing it at standard states, that's going to be 298 Kelvin. And then L and Q would be, remember that Q is just this, right? At standard states, Q would be 1 ATM. Well, natural log of 1 is 0. And then all of this multiplied by 0 is just 0, right? So, at standard states, delta G equals delta G with a little circle, which would be that. And that's kind of a duh, right? We literally define the little circle as standard states, which would be I input 298, I input 1 ATM for this, which you can't see because it's behind this thing here. So, not super exciting there, but this is where the standard state equation comes from. If I enter all ones for all my concentrations and all my equilibrium stuff, I always get Q equals 1. So, that's why we use it as a standard, so that this equation works out too. So, let's not use standard states because that's not super helpful to us, right? You're just going to get delta G equals delta G naught. So what we need to do is we need to select a different condition. A condition that is more appropriate for what we would experience, like, say, right now. So let's suppose that this is the water vapor pressure that we're experiencing. 5 times 10 to the minus 3. In other words, it would be like 0.5% of the atmosphere. I think, if I'm doing my math right. 2, 1. Yeah, okay. So let's figure out what delta G would be under these conditions. So let's get rid of all this again. Windows, no, I'm not updating in the middle of a stream. You can just go away. All right. So again, Q is going to be equal to whatever water pressure I have. But this time, it's going to be this really small number. And again, we omit the units for equilibrium constants or reaction quotients. So delta G will be delta G naught, which is still 8590, plus R times T. We're at what? 25 degrees Celsius? So 298 Kelvin times natural log of Q. All right, so where do our units go? So this Kelvin and this Kelvin cancel out. I'm going to have joules per mole and joules per mole. So my answer will be in joules per mole. So let's punch this all in the calculator. So I've got 8.314 times 298 times 5 times 10 to the minus 3, which I'm going to natural log. And that all those things multiplied together give me minus 13,126. I'm going to add 8590 to that. And so the result that I get for this is minus 4,536. So at these conditions, where the water vapor in the air is very, 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 very low, delta G for this is actually negative, which means that at 25 degrees Celsius, if there is this little water vapor in the air, the water should spontaneously evaporate. And we observe that. If you spill water at room temperature on a table, it will eventually all evaporate. And that kind of makes sense because, let's see here. If I take this number and I look at this expression here, so this is our expression. If we look at Le Chatelier, and we have very little of this, which direction will equilibrium shift? It will shift in this direction, right? And it will continue to do so until it is saturated. What does it mean for your air to be saturated? It will have all of the water vapor that it can hold at that temperature, right? Now, that's assuming it's a closed system. The Earth is not really a closed system, right? Like, the atmosphere is so humongous that we call it an open system. So, water will just generally evaporate within a local area. Now, if too much water is in the atmosphere and the temperature changes, then it will condense. This is called weather. And we know a lot about that up here. We get a lot of water vapor around Seattle, don't we? All of that water vapor then hits cold fronts and condenses, and then it rains down on us, and then we're just gloomy until June. Right? I'm so sick of the cloudy weather. Give me a 72-degree sunny day. Like, I don't even like the sun. I'll be sick of it in a week after we like actually have June or July or whenever actual summer is up here. Before, you know, the burning starts and everything is smoked out. But so the point of this discussion is that we can use this equation. It's not on the slide. Let me go back to, there we go. This equation right here to predict whether a reaction will be spontaneous at non-standard conditions. Yeah, it was really nice yesterday. It was a little chilly, though. Oops, there we go. All right, let's do one more problem here. At what vapor pressure of water would evaporation cease to occur? Now I'm going to put on here at 298 Kelvin. Because that does matter. We need to plug in temperature into our expression here. So, I didn't mean to put that on the screen yet because I was going to talk about it, but that's okay. All right. At what temperature would water stop evaporating? Or I'm sorry, not temperature, but at what water pressure? That's, I messed that up. Okay. So I'm going to write this down here. So if I have this process and water is no longer evaporating, then what that would mean is we have reached saturation. There's enough water vapor in the atmosphere that this process no longer occurs spontaneously in the forward direction. Once I hit some amount of water vapor pressure, this reaction reaches equilibrium. And if we're at equilibrium, this is true. So what we need to do in order to figure out what water vapor pressure we need to have in the atmosphere for evaporation to stop is we need to solve for this. Well, the only place that this shows up is right here, right? Because Q is just this number. And we know that at equilibrium this would be 0, so I'm going to set this equal to 0 and solve for Q. So we could do that. That's trivial to do. So let's get this out of the way so I have some space to work here. And we'll just work in blue. That's okay. So if I set this equal to 0, then my expression will become delta G equals minus RT ln Q. Oops, I forgot my negative there. So I could do that. And then to solve for Q, I just take e to the both sides, right? So e to the negative delta G over RT will equal Q. And we know that Q equals the pressure of H2O. That is water vapor. So let's do that. E to the negative delta G, so negative whatever delta G was at standard state. I've already forgotten the number, so I got to go back and look at it. Let's see here. That doesn't tell me it. Where is it? 8.59. Okay. Negative 8590 joules per mole divided by RT, 8.314, times 298 Kelvin. So those cancel, those cancel. Here's the thing about E and natural log. Anything inside of an E or a natural log should not have any units. All our units canceled out, so that's good. So we're going to do, let's see here, 8590 negative divided by parentheses 8.314 times 298. We're going to hit enter on that, and then I'm going to do e to the. So minus 3.467. So e to the 3.467. I think that was right? So I got this. (0.0312). And since that was a pressure, I should put this in there. And then just because I'm curious, how many torr is that? It should be like 23 point something. Yeah, 23.7. Okay. So at 25 degrees Celsius, this is the maximum amount of water vapor that I can have in the atmosphere. And if I go above that number, then water will instead condense as opposed to evaporate. And now if you look up the vapor pressure of water at various temperatures, do I have a table of this on Wikipedia? No, that's just vapor pressure of everything. There we go. And we go to Wikipedia. This is actually really cool. Looking up the vapor pressure of water here. Oh, it's like right over there and I can't see it. You will notice that at 25 degrees Celsius, that's the exact answer that we calculated. Pretty neat. In fact, what we just did is how they got the numbers in this table. And then this is the number I was checking because I know these numbers in Tor because I used to do stuff with water vapor all the time. But yeah, that's how we get those numbers. So we can calculate saturation temperatures by using this process, which is really cool, I think. So this is the part of the class where we start to get all of these applications of just stuff that we've sort of taken for granted, I guess. And as somebody who has an interest in meteorology and like temperatures and stuff at which water will condense and like how likely you are to get rain or whatever, you can use thermodynamics to figure that out, which is just kind of neat. It's a very Marge Simpson type thing for me with this stuff. I just think it's neat as I hold the potato. All right. What this chart is showing you is on the x-axis, I have a vapor pressure of water. And on the y-axis, I have my delta G, absolute value of delta G. And the reaction is going to try and minimize the absolute value of delta G, right? It's trying to head towards delta G equals 0. So over here, I have a negative delta G, and the reaction will proceed towards equilibrium. Over here, I have a positive delta G. The reaction will go in the reverse direction until I hit the just right point right here. So I don't really think these graphs are super helpful, but if it helps you imagine how delta G works, kind of like a function where it's just going to do this sort of thing until it settles at the bottom here, then that works for me. All right. I want to say that like we're done with the slides. Isn't this like all the slides? Where are we? Yeah, we're right here. Cool. Okay. Wait, no, we're not. We're right here. Okay, so we do have some more things to do. All right, let's do one more example, and then we'll take our break, because we're going to go a little bit over today, just because I want to make sure we have to be finished with Chapter 13. I want to start Chapter 14. So here's the types of problems that I'm going to give you for these questions, because it's kind of ambiguous, right? So like we can figure out boiling temperatures of things. We learn how to do that. We can figure out whether something will happen or not based on delta G versus delta G naught. What I want to ask you are questions of this nature, and I'm going to highlight the important part here. Is the reaction more or less spontaneous at the conditions I have given you? Now, the important part here is that in order for something to be more spontaneous, delta G will be more negative than delta G with a circle, delta G naught. To be less spontaneous, delta G will be more positive than delta G naught. And so that's going to be our goal. Can you calculate delta G and compare it to delta G naught, which I will give you for this? And if I don't give it to you, you can calculate it from Appendix G. Remember that we have delta G of formations in the back, and you can do products minus reactants, same as you did in 162. So let's do this problem together. We'll have you do the other problem after the break here. All right, scrolling up. There we go. So delta G is equal to delta G naught plus RT ln Q. The first thing that I would do for this reaction is I would say, okay, what is Q here? So Q, for the reaction as written, would be, so I've got NO2 as a product, There are 2 of them, so I need to square it. And then I've got NO. There's 2 of those, so I'm going to square it too. And I've got oxygen. And there's only 1 of those. So writing the equilibrium expression to get your Q is probably the most important part of solving this. The rest is just algebra. So let's do this. So I've got NO2 is 1.8 atmospheres, which I'm going to square, divided by nitrogen, or not nitrogen, nitrous oxide, 150 squared, times oxygen. And so when I do that, what do I get? So 1.80 squared divided by 0.150 squared times 0.125. That looks good. Equals 1,152. So there's my Q. I reduced it to 3 sig figs because of all my numbers I put in there. And so now I can plug in the rest of the expression. So delta G is going to be delta G naught, which is 71,200, plus RT, what temperature are we at? 298 Kelvin, okay. Times natural log of Q. So let's see here. So 8.314 times 298 times 1150 natural log is that. And then I'm going to subtract 7,000 or 71,200. So that's what I got. Minus 53,700. All right. So I concluded that delta G for this reaction at these conditions is more positive. So delta G is more positive than delta G not. So the reaction is less spontaneous at these conditions. Now, is it spontaneous? Yeah, it is. The reaction will still go in the forward direction, even with these concentrations of things put in there at this temperature. But it will not be as spontaneous as if I had put in 1 atmosphere of everything. All right. So hopefully that makes sense. All right. And again, if we go back and look at Le Chatelier, this makes sense because standard conditions would just be 2 ATM, 2 ATM, and 1 ATM. And relative to the amounts of things that I put in there, standard state pressures are way higher on the reactant side. So I have very, very, very few reactants relative to standard states. So my reaction should be less spontaneous than if I had more reactants. All right. We're going to take our break here. So let me put this on the screen. Oh, I got to get the timer up. So we'll still take a 10-minute break. Let's see here. Oops, I don't want this to pop up here. Let me make sure my music actually works, because everything is exploding today. All right, so we'll do that, and then I will push this button and enjoy the music for 10 minutes. So see you in a bit. I didn't realize my mic was on, sorry. I'm sitting here adjusting shit and you can hear that. There we go, sorry about that. I'm sitting here, like, moving my tablet around here and trying to organize my working space here. Everybody can hear me. Hopefully I wasn't talking to myself, because I tend to do that. All right. On the screen here, I want you to do the exact same thing that we just did. Tell me if this reaction under these conditions is more or less spontaneous based on this delta G. And my hint for you is that this right here, where it says rhombic, this means solid. The reason that we're indicating that it is rhombic is because there are different solid states for sulfur. There is the rhombic state, which is it crystallizes in a sort of like, I mean, it makes a rhombus, sort of more like a parallelepiped, I guess. And then there's another solid state that I can't think of off the top of my head. I think it's S8 is the solid state for that. It's molecular. So use these numbers that I've given you, and I want you to tell me more or less spontaneous under the conditions as shown relative to standard conditions. I want you to type your delta G value that you acquire in the chat once you get it. I'll give you about 5 minutes, and we'll go over the results then, so see you in a bit. All right, one more minute. We'll go over the answers. All right, let's go over the answers. First, I have to get the cat out of the way. Oh, no, Maya, don't do that. There you go. You want to say hi to the class? No. She just wants to be pet. Maya, we have to do a practice problem, though. So we got this. We'll just shove that off the screen there. Okay, so first let's write out Q for our expression here. Maya loves everybody. So that would be, so we got sulfur, which is rhombic, but that's a solid, so we won't include the solid. So we got H2O. And there's two of them, so it's squared. Then I got H2S, which is squared. And then SO2, which is just 1. And so that's going to be, so what was my water vapor? 0.01. Divided by H2S is 2, so that's 2 squared times SO2, which is 1.5. All right, I'm going to get a tiny number for this, it looks like. 0.01 squared divided by, well, 2 squared is 4 times 1.5. So 1.67 times 10 to the minus 5. So there's my Q. And so let's plug all that in. So delta G equals delta G naught, which is minus 102,000 joules per mole, plus RT I'm assuming this is 298K and I just covered that up. Yeah, it is. Okay. Oops, hold on. Oh, that was silly of me. Now I gotta go back over here. There we go. Times natural log of 1.67 times 10 to the minus 5. So, calculator, 8.314, 298, 1.67 times 10 to the minus 5 natural logged. And then I'm going to subtract 102,000. 129.25, is that what I got? So 129,000 joules per mole. I mean, that's close enough to what you got, Alexa, so I'm going to say that. I might have hit the wrong number when I typed it in, but that's okay. The point is, delta G is more negative than delta G circle, delta G naught. So, more spontaneous at these conditions. And that makes sense because, again, standard conditions would have been 1 atm for everything. So let me just write that next to all these. So 1 atm, 1 atm, 1 atm. And so what I ended up doing was I reduced the pressure of water a lot, and I increased the pressure of these two a lot. These were both reactants, and this was a product. So it makes sense, according to Le Chatelier, that this reaction would be more spontaneous because I filled it with reactants and I removed all the products, basically. So Le Chatelier backs this up, that like, hey, it should be more spontaneous, right? And it totally is. All right, last thing we can do in this chapter, we figured out from a previous experiment, or example, I should say, that there was a certain vapor pressure at which the evaporation of water was at equilibrium, and that value was where delta G of the reaction was 0. And if it's at equilibrium, whatever you get for Q is going to be equal to the equilibrium constant, right? So if that's true, and I take this expression and I go, okay, I'm going to put this as 0, and this is just K, then I just move this to the other side, and I get delta G naught equals RTL and K. Minus RTL and K. Sorry, I forgot the minus there. And so what this lets us do is this lets us take thermodynamic values from Appendix G for any reaction I want to, and I can figure out its equilibrium constant. Now, the equilibrium constant and the temperature are going to be linked together. So whatever constant I generate, I'm going to have to link it to a particular temperature. So if I pick 298, I will get the equilibrium constant at 298. If I pick a different number, I will get a different equilibrium constant. Now, these delta G values are at standard state, so this is going to be most accurate at 298 Kelvin. If we pick a different temperature, it will still be fairly accurate, but we're still going to have we're going to get a little bit of error as we deviate from 298 Kelvin, because our delta G of reaction for these types of problems will be based off of data, like the delta H and the delta S data will be from 298, which is how we got delta G. Now, for any reaction where we are asking, hey, is it spontaneous or non-spontaneous? Remember that if I have a K greater than 1, that means that my reaction is shifting towards products, right? I mix the things together and then I'm going to end up with mostly products. So that means it's spontaneous in the forward direction, because the forward direction points towards products. If I have a K that's less than 1, then the reverse reaction is spontaneous. And if I have a reaction that K is equal to 1, I'm just at equilibrium. Now, these are all, again, at standard states, which again means 1 molar solutions, 1 atm of pressure, 25 degrees Celsius, etc. So if I just create a mixture with everything at standard states and then I tell it, go, it will move in the direction based on whatever the equilibrium constant is. If it's bigger than 1, it's going to go in the forward direction. If it's less than 1, it's going to go in the reverse. Oops. So I have some pictures of that here. The dotted line represents, in the middle, my standard state solution, which is 1 atm of everything. I don't really like how the wording is not centered over the line, but it's doing that so it doesn't cross over the red line. And again, the y-axis is the absolute value of delta G. for whatever given condition it is. Actually, so this should just be, let me erase that. There we go. Since it'll only be delta G circled at the center. All right. So let's do an example. What is the equilibrium constant for this reaction at 298 Kelvin? So now I'm giving you Appendix G data for delta G of this of each of the substances. So I'm giving you delta G's of formation. So to find delta G of the reaction, that would be products minus reactants, which would be, so I have NO2, and I have 2 of them, so that would be 2 times 51.3 kilojoules per mole minus an N2O4, and I only have 1 of those, so 99.8 kilojoules per mole. So remember that when we're doing these sorts of things, if we have multiple of something in the reaction, I got to multiply it by the number for the coefficient that shows up in the reaction. So this is because of the 2 coefficient that's there. So what do we get? 2 times 50, that's not 5, 51.3 minus 99.8. All right. So there's my delta G of the reaction. And I know that delta G equals minus RT, natural log of the equilibrium constant. So I'm going to solve for K. So I'm going to do, this becomes minus delta G over RT equals natural log of K, which then becomes e to the minus delta G over RT equals K. And so e to the negative this number, so negative 2,800 joules per mole. I'm turning it back into joules per mole at this point because now I got to work with R here, right? And we're at 298 Kelvin. So joules per mole cancel, my kelvins cancel. That's going to equal my equilibrium constant. And so K will be whatever this mess is. So let's go over here. E to the parentheses 2800 negative divided by parentheses 8.314 times 298. Close, close, close. And I get 0.32. So that tells me that if I put my mixture of reactants and products in here, when the reaction has reached equilibrium, it will be mostly reactants. I will have mostly N2O4 in the mixture. All right. So I want you to do that. I want you to tell me what delta G for this reaction is without looking at Appendix G. Instead, I have given you the equilibrium constant. So go ahead and do that. And we'll go over the answers in just a second. All right, one more minute, we'll go over the answer. All right. So for this one, delta G equals minus RT natural log of K. So that's going to equal minus 8.314 joules per mole Kelvin times 298 times natural log of K. So that's pretty straightforward. You're just plugging it into the equation. So 8.314 negative times 298 times 81.9 natural logged or you get that. All right, very good. So really, these types of problems, I'm going to give you the formula, and you're going to have to solve for either one thing or the other thing. Either delta G or K. Obviously, solving for K is more difficult because K is buried in the equation. Solving for delta G is pretty easy. All right. I believe that's it for Chapter 13. Hooray. Okay. So something to note about the quiz. So your quiz can be turned in this week now. On the quiz, I just had this. I was just thinking about it. What did I want to say about it? What did I want to say? I had something I wanted to say about the quiz, but now I can't think about it. That's okay. Anyway, what you're going to want to do for your quiz is you're going to want to turn it in either online using the Google Sheet or make it a PDF or whatever. Or you can turn in a paper copy to me on the day of the lab. So it'll be due this Friday. You can use whatever method you'd like. You won't get them back during the lab because I have all the rest of them to grade back. But what I will do is I will have them available for you the following week if you would like them. If I do manage to grade them that day, what I will do is I will... this is only really particularly important for exam week, but during exam week, I will put them on in like an envelope outside of my office door for people to pick up if they would like, or something like that. Okay, so I said we were going to go for like 10 or 15 more minutes real quick, so let me get the next slideshow up here. Let's move on to Chapter 14. So Chapter 14 is kind of the biggest chapter in this course. The other ones are not anywhere near as big. So we're going to be here for a while because there are 171 fucking slides, my goodness. There's a lot to do here. All right, we're going to introduce acids and bases today. So that'll be where we start. And then what we're going to do from there is we're going to do all sorts of calculations involving equilibrium. Because everything that we talked about in Chapter 13, calculating the equilibrium constant, doing the calculations where x is small, that sort of stuff, that's going to be super useful for this chapter for us to figure out a property called pH. And pH is going to be very useful for us to understand both physiological systems like the body, and also various like chemical activities, how proteins interact with stuff like that, conditions for a reaction to go, etc. So let's introduce acids. What is an acid? An acid is any substance that has all of these principal properties. So the first property is that if you taste it, it tastes sour. Your tongue interacts with acids in a manner that we perceive as sour. So something like a lemon or a lime or even like grapefruit. I'm trying to think of sour fruits. There are sweet fruits out there, so like orange. Like orange has a bit of a tang, a tartness to it. That is due to acid. Soda pop also has this. If you drink seltzer water, your seltzer water has a bit of like a tang after you drink it. Oh, there it is right there. I had to taste it to believe it myself, I guess. But that taste that you feel, that it's like a mild burning, I guess. That is the acid interacting with your tongue. Now, acids will dissolve metals. The higher the concentration of the acids, the more capable they are of doing that. So things will corrode in the presence of acids. And we'll talk about some inorganic applications of that, such as why you shouldn't make things out of marble and then put them out on display in Pittsburgh later on in the chapter. That seems very specific, but there's a reason for that. Now, there is a special type of paper. It's called litmus paper, and litmus paper interacts with acids and then their counterpart bases. Blue litmus paper will turn red when exposed to any sort of acidic compound. And then the last thing that we care about for acids is that they are capable of neutralizing a base. Now, where do you find acids? Acids are all around you. You have acid in your stomach. It's called stomach acid. Now, naturally occurring acids would be things like citric acid or tartaric acid or acetic acid in vinegar. These are all things that we have around us. We tend to enjoy them. We consume them. We use them for flavoring on foods, or sometimes they are just part of the food themselves. There are other acids that are industrially important. HCl and H2SO4 are very common ones. Nitric acid is another common one. I think I have a slide. Yeah, here we go. These are a bunch of different acids that are available either commercially or are abundant in the environment. Of the environmental ones, the most abundant and common one I would say is this one right here, carbonic acid. Carbonic acid forms naturally when CO2 reacts with water. You get H2CO3. This is how you carbonate beverages, and why carbonated beverages have a little bit of a kick to them for your tongue. It's because the CO2 acidifies the water. Now, this also prevents an environmental concern. Not carbonated beverages, but the same process. If there's too much CO2 in the atmosphere, then the ocean becomes a carbonated beverage, and thus would be acidic. And it turns out that aquatic life, like dolphins and whales and fish, really don't like seltzer water because they breathe that stuff, right? If you were a fish, you were breathing the water to get the oxygen out of it, the little that's dissolved in there, and then you are expelling CO2. If you fill the water with CO2 in the form of carbonic acid, you're basically suffocating fish and marine life. So, not great. We don't want to fill the ocean with CO2. Of these acids, I would actually say that the most dangerous to your health is this one, which, if you spilled the sodium fluoride and then got it wet and then, touched it, you exposed yourself to this, hydrofluoric acid. Hydrofluoric acid is rather dangerous because fluoride is it loves calcium, and there's a lot of calcium in your body, and it will just neutralize it. And neutralizing calcium and making a precipitate in your veins and arteries, probably not great. So, avoid HF if you can. It can be very bad. The other ones are just corrosive, so they will provide you with burns if you contact them. But some are safe for consumption. So, for example, vinegar is safe to eat. Citric acid is safe to eat. Phosphoric acid is the flavoring agent that is in Pepsi and Coca-Cola, and is responsible for its very low pH of 2. We'll talk about what that means later. Here are some structural diagrams of acids. The feature of the acid, which we're going to talk about in just a little bit, that makes it an acid is this. There is an H on each of these molecules. Some places there are multiple H's. I don't know why I'm circling the formula, I realize. That can pop off of the molecule. So I would just get this. So boop. So there's my acid. And then I get whatever else is left over. And all of these can do this. So this can do boop, there's my acid. And then whatever else is left over. Now, not all H's are acidic. For example, these right here are not acidic, and that's because the CH bond is strong. You'll notice that there's a very common feature here. A lot of these H's that are acidic are bonded to oxygen. The OH bond, depending on the circumstances, is not as strong as you might think it is. The reason being, oxygen loves electrons. Its electronegativity is super high. And so, when it sees these electrons bonded to a hydrogen, it goes, I think I'd rather have these for myself. And then it just kicks off the H+. so that it's all by itself, alone and destitute, like Oliver Twist or something. I don't know. Oxygen, you bastard. All right. This is a special group that I've circled. Whenever you see this arrangement of atoms bonded like this, C double bond O, bonded to an OH, this functional group tends to be acidic. This is called a carboxylic acid. And the reason that this tends to be a very acidic group is that because you have two of these oxygens right here. And I don't know why my pen does that. They tend to draw electrons towards themselves. And that means expelling that H as H+. You're going to see carboxylic acids all the time in 261, Chem 261. Because they are a very important functional group in organic synthesis and organic chemistry, and particularly in biology. Carboxylic acids are everywhere. All right. That's it. Those are acids. Let's talk about bases. What are some properties about bases? Bases don't taste sour. They trigger a different response from your tongue, and that response is bitter. So I got to use this picture of this girl again going, bleh. Bases taste very, very bitter. They may also taste a little bit chalky. Examples of things that are bitter would be things like caffeine. If you've ever tasted pure caffeine or had something like, say, the example I keep coming back to is in college, my buddy had breath mints that also had caffeine in them, and he would offer them to me because our chemistry class is at 9 a.m. And I was a night owl, so I would always be extremely tired, and so I would accept them. And that would wake you up real quick, but also what I ended up realizing was that caffeine is super, super, super bitter. Like, holy crap bitter. I can taste caffeine now in Pepsi and Coca-Cola because of those mints. Trying to think of other things. You don't really eat bases is the thing. So the bitter taste is not a great flag for us to identify them. Cocoa, for like if you've ever had like bittersweet chocolate or pure chocolate, it's extremely bitter. Because there is a compound in it that is a base. This is a much more appropriate tell for a base. Bases feel slippery, and there's a very specific reason for this. When you interact with bases, your hands, which contain things like fats and grease and oils and stuff like that, interact with the bases and undergo a process called saponification. In other words, they are reacting with the base. So when you are using soap, like maybe when you scrub yourself with soap in the bath or the shower, and your skin feels all slippery, this is because the soap is reacting with the top layer of skin and dissolving it. So soap actively dissolves your flesh, and that's how it cleans you. Now, that's okay because the top layer of skin is dead anyway, and you don't want it, right? Like, you can just wash that shit away. But it is reacting in a way that makes your skin cells more soluble in water and can be washed off. So, enjoy that thought. Just like acids turn blue litmus paper red, bases turn red litmus paper blue. And then finally, bases neutralize acids. Bases and metals don't tend to do a ton. There are some reactions, but they're not as prolific as acids. Acids are very good at reacting with metals. Now, there are not very many foods that contain bases, but they do exist. They are things that taste bitter. Usually we encounter bases as cleaning products for the aforementioned reason that if I want to clean something like grease or grime or dirt or whatever, and it has fatty acids on it, I can react the fatty acids with a base to neutralize them and make them soluble. So soap is made with a base. Here are some examples of common bases. Medicinal bases would be things like carbonates. So sodium carbonate is also known as Tums. You may actually have it as calcium carbonate. Calcium carbonate is also chalk, which is why I said that they have a chalky sort of texture and flavor to them. Other bases are things like lye. Li is sodium hydroxide, so this is Li right here. And then another common base is ammonia, which is used as a sort of detergent. We can use it as something for cleaning. We also use it for fertilizer in plant maintenance and care. Ammonia is very, very important industrially, and we're going to see a lot about ammonia as we go through this chapter because it is one of the most common bases. However, it is a little bit strange to it. You'll notice that a lot of those bases up there have oxygen. Most specifically, they have an OH in there. But ammonia doesn't. And when we come back on Wednesday, we're going to talk about exactly why that is. So that's our introduction for acids and bases. Just a little general, like, how do you do with them? Yeah, so when we come back on Wednesday, we're going to discuss them in more detail. We're going to talk about conjugates. We're going to talk about pH. We're going to show some equations for calculating. And then we're going to get into some acid-base equilibria calculations so that we can start exploring all the crazy things that we can do with acids and bases. And there are a lot of them. So look forward to that. Thank you for coming out to the lecture. I apologize for all the technical difficulties that I had earlier today. I'm going to have to just pay attention to that, see if when I boot my computer up, the webcam hijacks everything and says, haha, I'm not going to detect your microphone. Yeah, that's all I have. So make sure you get that quiz in for Chapter 13. It is due on Friday. You can bring it to the lab or turn it online. Lab worksheet number 1 is also due Friday. We'll see you on Wednesday. Take care.